Welcome to the deep dive. Today, we're really taking a plunge, getting into the fundamental knowledge that, truly underpins our whole digital world. So if you've ever found yourself wondering what actually happens behind the screen when you click a button, maybe, or what it really takes to build the apps we use every single day, well, this deep dive is definitely for you. Our source material for today, it's straight from the Byte Go newsletter, which is honestly a fantastic resource for anyone looking to get smart and fast on these essential concepts in backend development and system design.
Yeah, it's a gold mine. And our mission here, as always, is really to pull out the most important nuggets of knowledge from these sources. We're basically offering you a shortcut, a way to get well informed about these key areas: back-end architecture, version control, modern deployment stuff, and even how giants like Netflix build truly massive scalable systems. It's all distilled down for clarity, giving you the insights without just overwhelming you with information.
That's absolutely the goal, and we've got some exciting topics lined up. We're going to cover mapping out the core skills needed for backend development, really understanding the practical steps of Git, exploring those crucial differences between virtualization and containerization, which is super relevant today, and even taking like a fascinating peek under the hood at how Netflix handles just immense amounts of data using this clever distributed counter thing.
Okay, let's unpack this.
Yeah.
Right. So let's kick things off with what Go calls the How to Learn Backend Development mind map. I kind of see this less as just a list, more like a structured blueprint, yeah.
Yeah.
It really lays out the technical foundations that power, well, pretty much every application we touch.
Exactly. And that first major block on the map,
Okay.
fundamentals. This isn't just definitions, it's the bedrock. We're talking about, the difference between backend and front end, how the client server model actually works, and the role of DNS, which is often overlooked but absolutely critical.
DNS, right. People forget about that sometimes. They do. But it's so fundamental. I
Yep.
mean, ask any experienced developer. When things go wrong in production, DNS is often one of the first places they look. If it's broken, nothing else works. Simple as that.
Makes sense. Okay, so from those fundamentals, the roadmap branches out into backend programming languages. And what's interesting here, I think, is just the sheer variety. The sources list,
Right.
like Java, Python, JavaScript, Go, Rust, C Sharp. It really shows there isn't one single right answer.
No, definitely not. It's more a spectrum of tools,
Yeah.
right? Designed for different kinds of problems, different team preferences.
Yeah.
And that language choice often connects directly to the next big pillar, databases, which are, absolutely central. The source material does a good job breaking down the types. You've got your SQL databases, Postgres, MySQL, great for structured data, complex relationships.
They're traditional workhorses.
Exactly. Then NoSQL options, MongoDB, DynamoDB, they excel with more flexible, maybe unstructured data and scaling out horizontally. And even these new SQL databases like CockroachDB, which are sort of trying to blend the best of both worlds. Yeah. And beyond just storing data, the map rightly points out ORM's object relational mappers, which kind of smooth out how your code talks to the database. And database caching too. Both are absolutely vital for managing data efficiently, especially under load, keeping those reads and writes fast.
Okay, then we move on to APIs and web services. And this, for me, is where it gets really interesting because it's all about communication, right? How different parts of an app or even totally different apps talk to each other.
Precisely.
We're talking API types like REST, GraphQL, gRPC, SOAP, lots of acronyms there.
Yeah, always.
But it's not just what they are, it's how you secure them. Things like JWT, OAuth 2, simple API keys. The source highlights how crucial these authentication methods are.
Absolutely crucial. They're not just technical details. They're the actual contracts, the security gates that let the digital world connect safely. Following that, we dive into server and hosting. So where does this stuff actually live? The source points to the big players, the major cloud providers, AWS, Azure, Google Cloud Platform, kind of the foundation these days for many.
The usual suspects.
Yeah, but it's not just picking a cloud. It's also about understanding how things like containerization using Docker and Kubernetes have become so dominant for deploying applications now. And you still need robust server setup, tools like Nginx or Apache acting as web servers, reverse proxies, managing traffic efficiently. What's fascinating is seeing how all these pieces devote the code, the database, the APIs, the servers, the cloud, fit together to actually bring an application to life and make it available globally.
And finally, wrapping up this whole backend mind map, we hit DevOps, Which isn't just a buzzword, right? It's a critical discipline.
Oh, totally. It's about making sure your application actually gets from a developer's laptop into production smoothly, reliably, repeatably.
So what are the key parts there, according to the source?
Well, it outlines things like CI/CD pipelines, continuous integration, continuous deployment, using tools like GitHub Actions or Jenkins to automate testing and deploying code. Then there's infrastructure as code, or IAC, using tools like Terraform or Ansible to manage your servers and infrastructure with code, not manual clicks. Super powerful.
Repeatable infrastructure.
Exactly. And finally, robust monitoring. Tools like Prometheus, Grafana, the ELK stack, Elasticsearch, Logstash, Kibana, these are essential for keeping an eye on things, collecting metrics, visualizing performance, analyzing logs, basically understanding the health of your application in real time.
Wow, that's a really comprehensive blueprint. It covers so much ground for understanding how the internet actually works behind the scenes. But okay, once you have these building blocks, how do you actually build stuff, especially with other people? That brings us squarely to Git.
Git. Yes.
The source material hammers home how essential this is. It's framed as like the unseen backbone of modern software development.
Couldn't agree more. And the source provides a really clear, simplified Git workflow. It's elegant, actually.
Yeah.
What's key isn't just memorizing commands, though. It's understanding the why behind each step, how it enables controlled collaboration.
Okay, walk us through it.
All right, so you start in your working directory. That's just your project folder where you're making changes to files, standard stuff. Now, when you've made some changes you're happy with, maybe fixed a bug or added a feature, and you want to sort of prepare them for saving, you use git add.
Okay, Git add.
This moves those specific changes into what's called the staging area. Think of it like a waiting room or a draft space. It lets you precisely choose which changes will go into your next official save point. You don't have to commit everything at once.
Right, so you're curating the commit.
Exactly, meticulously staging them. Then, once you're ready, you use git commit your descriptive message. This is the crucial step. It takes everything in that staging area and saves it as a permanent snapshot in your local repository. It creates a point in your project's history, marked with your message, explaining what changed. It's like taking a photo.
And that's all just on your own machine so far.
Correct. That's your local history. Now, to share that work or back it up somewhere else, you use git push. Git push uploads your committed change, changes those snapshots from your local repository up to a remote repository. That's often on a platform like GitHub, GitLab, Bitbucket. Makes it visible to your team.
Okay, pushing changes out. What about getting changes in from others?
Good question. Two main commands there. Git pull is common. It does two things. It fetches the latest changes from the remote repository, and it automatically tries to merge them into your current working branch. Convenient, but sometimes too automatic.
Uh-huh. What's the alternative?
For more control, especially if things might conflict, you can use git fetch. This just downloads the remote changes but doesn't automatically merge them. It lets you see what's changed first, maybe using git diff, before you explicitly decide to merge those changes into your branch. Gives you a chance to review.
Okay, that makes sense. Fetch, then merge for more control.
Precisely.
Yeah.
And you mentioned git diff. That's super useful. Git diff head, for instance, shows you exactly what's different between your current working files and the very last commit you made. Great for reviewing before you even stage things with git add.
It's actually amazing how these, 5 or 6 core commands form the basis for how millions of developers collaborate every day.
It really is quite elegant.
So what this all means for your workflow essentially is having a safety net. You can track every single change, experiment without fear because you can always go back, and coordinate really complex work with a team, big or small.
Absolutely fundamental skill.
Okay, so we know how to build the backend components. We know how to collaborate using Git. Now let's talk about getting these applications deployed out into the world. We need to tackle 2 really crucial concepts that have totally reshaped modern infrastructure: virtualization and containerization. Understanding the difference here is key.
Oh, definitely. They sound similar sometimes, but they operate quite differently. Let's define them clearly. Virtualization. This is about creating multiple virtual machines, or VMs, on a single physical server. Each VM acts like a whole separate computer. It gets its own operating system, its own virtual hardware, all managed by a piece of software called a hypervisor.
Like partitioning a hard drive, but for a whole computer?
Sort of, yeah. The big advantage is strong isolation. Each VM is pretty separate from the others, like having physically separate machines just running on the same hardware.
Okay, got it. VMs. What about containerization?
Containerization is different. It's generally a much lighter weight approach. It lets you run applications in isolated environments called containers, but, and this is the key difference, all the containers on a single host machine share the same underlying operating system kernel.
Ah, so they don't each need their own full OS.
Exactly. Instead of separate houses, think of them more like separate apartments within the same building, sharing the foundation and maybe some utilities, but still self-contained units.
Right.
A container engine like Docker manages this.
Okay, that distinction seems important. The source material then lays out different ways you might deploy.
Yes. It gives a nice spectrum.
First, there's bare metal, just running your app directly on the server's OS, no virtualization, no containers.
Right. Maximum performance, potentially, because there's zero overhead from virtualization layers. But it's inflexible. You're stuck with that OS. It's harder to manage multiple apps without conflicts. Resource utilization might be poor.
Then the virtualized approach we just talked about, using a hypervisor, creating those VMs, each with its own guest OS.
Yeah. The benefit is that strong isolation. Great for running totally different operating systems or apps that need very specific environments or legacy stuff, but it uses more resources, RAM, disk space, because each VM needs a full OS.
More overhead.
More overhead, definitely. Slower to boot up too, usually.
Then containerized,
Yeah.
using Docker or something similar, sharing that host OS kernel.
This is where you get the benefits of being lightweight. Containers start up way faster, use fewer resources, you can pack more of them onto a single server. It's much more efficient.
Which makes it great for things like microservices.
Exactly. Perfect for microservices, cloud-native applications, where you want density, speed, and consistency in deployment.
And finally, the source mentions a hybrid, containerized on virtualized, running containers inside VMs. Why would you do that?
That's actually super common, especially in cloud environments. Think about it. You get the strong isolation and maybe the security boundary of the VM from the hypervisor.
Okay.
But inside that VM, you get the efficiency, speed, and packaging benefits of containers for your actual application deployment. It's a way to balance those different needs. Flexibility and isolation from the VM, efficiency and speed from the container.
Right. Kind of the best of both worlds in some scenarios.
Yeah, it offers a powerful combination, especially for security or managing diverse workloads within a larger infrastructure provided by, say, a cloud vendor who gives you VMs to start with. So this really raises that important question. Which approach is best? And why does this distinction matter so much today?
Yeah, what's the takeaway?
The takeaway is it's all about trade-offs. There's no single best way. VMs shine for strong isolation, running diverse OCs, legacy apps. Containers are champions of efficiency, speed, density, perfect for modern microservices and cloud-native patterns. Understanding this isn't just academic. It directly impacts your costs, your deployment speed, your resource usage, and how you design systems to be resilient and scalable. It's a fundamental choice.
That leads us perfectly into a really fascinating real-world example of tackling scale, how Netflix built something they call a distributed counter abstraction. This is a deep dive into some pretty sophisticated system design, showing how these principles we've discussed actually play out at massive, massive scale.
Yeah, this is where theory meets intense practice.
Yeah.
So first off, what is a distributed counter?
Yeah.
At its heart, it's a system where counting events like views, clicks, whatever, isn't done by one single machine because that would quickly become a bottleneck. Instead, the counting responsibility is spread out across many different servers or nodes.
And why does Netflix specifically need this?
Oh, imagine the scale. They need to track billions, maybe trillions, of user interactions in real time. Views starting, views stopping, thumbs up, thumbs down, items added to lists, all sorts of things. This data isn't just for historical reporting. It feeds into real-time decisions, like personalization algorithms, and helps them monitor and optimize their massive infrastructure constantly. They need to measure the pulse of their entire system accurately and fast.
Okay, so how did they build it? The source mentions 4 main layers, right?
Yeah.
Designed for performance, scalability, and this thing called eventual consistency.
That's right. Let's break it down. Layer 1 is the client API layer. This is the front door. How users, or more likely other internal Netflix systems, interact with the counter. They send simple requests like add count, increment a counter, get count, read its value, or clear count. These requests hit the Netflix data gateway, which handles routing and processing efficiently.
Pretty standard API interaction to start.
Yep. Then layer 2, event logging and time series storage. When an add count event comes in, it doesn't immediately update a central counter. Instead, the event itself is logged. It gets stored in what Netflix calls their time series abstraction, which is built for huge scale. Crucially, each event gets an event ID. Why? For idempotency.
Idempotency, meaning you can process the same event multiple times without messing up the count?
Exactly. If a network issue causes a retry, you don't want to count the same view twice. The IDE prevents that. And to handle the sheer volume and avoid overwhelming any single database node, these events are cleverly grouped into time-based partitions or buckets. All this raw event data gets stored in Cassandra, a distributed database known for handling writes at scale.
Okay, so events are logged safely first. What happens next? Aggregation.
Right. Layer 3 is the roll-up pipeline, or aggregation. This is where the actual counting happens, but in batches. Dedicated roll-up queues pick up these logged event changes. The key insight here is that they process these events and perform aggregation within immutable time windows. Say, aggregating all events for counter X that occurred between 10:00 a.m. and 10:01 a.m. Once that minute passes, the input for that window is fixed.
Ah, so the calculation for that window is stable and accurate.
Precisely. It avoids race conditions and complexity. This aggregated data, the actual counts for each time window, is then stored in another Cassandra store, the rollup store. This store operates under an eventual consistency model, meaning updates might take a short time to propagate everywhere, but eventually all nodes will agree on the count for that past time window. It prioritizes availability and scale over immediate, perfect consistency.
Okay, eventual consistency. That's a common pattern in large distributed systems.
Very common. And finally, layer 4, read optimization, cache, and query handling. Reading directly from Cassandra all the time might still be too slow for some uses. So those aggregated counter values from the rollup store are heavily cached in EV Cache, which is Netflix's own distributed caching layer built for super fast reads.
So when someone asks for a count, they likely hit the cache.
Most of the time, yes, for ultra-low latency. And there's a background process that continuously performs these rollups and proactively updates the cache, trying to keep the cached values reasonably fresh even before someone explicitly asks for them.
Wow, that's quite an architecture.
It is. And the performance figures are impressive. The source mentions processing something like 75,000 requests per second, with latency in the single-digit milliseconds for reads hitting the cache.
Incredible.
And if you connect this back, it really demonstrates the power of thoughtful distributed system design. It leverages ideas like idempotency, time-windowed aggregation, eventual consistency, and aggressive caching, many of the concepts we touched on earlier, to solve a real-world problem at unbelievable scale.
What an incredible journey we've had in this deep dive. Seriously, we've unpacked that really comprehensive roadmap for backend development. We explored the practical, like day-to-day essentials of using Git for collaboration, clarified those critical distinctions in deployment virtualization versus containerization,
Yeah.
and even got that peek into truly advanced system design with the Netflix distributed counterexample. It's been a lot.
It has. And it's fascinating, isn't it, to see how these topics, which might seem separate at first glance, are actually deeply interconnected. They really do form the fundamental backbone of the digital infrastructure we all rely on. Understanding these concepts, even at a high level, it isn't just about technical trivia. It's genuinely empowering. It helps you navigate, understand, and maybe even contribute to this tech world that's all around us.
Couldn't agree more. It demystifies things. And so, as we wrap up, I want to leave you, our listeners, with a final thought to chew on, building on everything we've discussed today. Given how incredibly rapidly technology keeps evolving, what foundational concepts do you think will be the most crucial ones to really master over, say, the next 5 years? What will it take to stay truly well-informed in this world of back-end development and system design as things keep changing? Something to think about.